So good afternoon, students. Today we will continue with the properties of material lecture, and we will be learning a few more aspects of how important this subject is. So mechanical properties, which you have seen in the previous class, they are more important in understanding and predicting the behavior of a particular material under the loads which will be coming maybe on a product, maybe on a building. Okay. So the quantities of force, stress, strain, strength, toughness, hardness, all these properties you have come across, friction, wear, it can help to identify the properties of material, which may be a metal, which may be a polymer, which may be a ceramic. So you can see here, initially, if this is a bar and there is a stress element or the element of the material, we'll be taking as a Q, and if we see it, so these are the molecular structure. So if we apply some load, so it will go under the deformation delta. Okay, and this molecular bonds will be stretched, or you see this will be taking a different shape. And when we remove this load, so this returns to initial. So this is a case of elastic means which is reversible. So when you have applied load, because of the load, there is a deformation, there is disturbance of the bonds. Okay, and when you remove that load, unload it, they return to the initial position. So that means the elastic means reversible. So if you see here, force versus displacement. So when you have applied the load from 0 to this value, so it increases in the elastic region. And when you release the load, it will come back to the original position. So this is a linearly elastic, and this is non-linear elastic. Means some kind of deformation will be retained. So although it is not state, you see, initially it is 0, then after applying certain load, it is so much, and then even if you it remains constant. Okay, then if you increase the load, it increases only a small portion. So this means the even if you have not increased the load, some extension or some deformation has taken place in this stretch. Okay, so this is a linear elastic behavior, and this is a non-linear elastic behavior. So common states of stresses. So we have seen a simple tension. So it is a sky lift. So here you see this is a cable, okay, on which this wheel moves. So if we take the simple drive shaft, this drive shaft. So if you see in the cable, the force is towards outside. A0 is the cross-sectional area when unloaded. So the stress will be equal to force upon the cross-sectional area, and we will represent it this way. Similarly, in order to understand the shear, so this is a shaft. So this shaft is, uh, under the influence of the moment, which is in the opposite direction. So this is a stress element or a small element we have taken. So this is an element whose area is A0. So this area is A0, and you see these are the shear forces. So it is complementary. So this is a stress on these opposite this thing, and you see this will try to develop a couple which is clockwise, and this force which is complementary shear force, it will try to develop a couple which is anti-clockwise. So if they are of the equal distance. Okay. So you can see this is a way we represent a shear stress, and this is a way we represent a nominal stress. So shear stress is you see the force divided by A0. So the shear stress in this case can be given by this. This we will learn. So engineering stress also we call it as a nominal stress or these two stresses. Then the tensile stress, if it this force is outward, so this is the tensile stress. You can see this is an area. So original area upon this, and shear stress you see. So this is a tangential component which is perpendicular, and this is a shear component, or the resultant is F if a force is acting at a angle. Okay, the area, cross-sectional area is same. So you see on this side it will be on the opposite side. So the shear stress will be Fs upon A0. Okay. So the stress has the unit Newton per meter square, or this we don't use nowadays, it is pound per inch square. Now you see a simple balanced rock. This is a picture of a balanced rock at the national park. So you see this piece is under applying a compression, okay, and it is a balanced one. So that means whatever weight it is exerting on this, exactly the same amount of reaction is there. So that's why it is in the same this. Okay. So compressive structure we have F upon A0, and we will represent this with a symbol like this. Then we have that was a uniaxial tension. Uniaxial tension means it is in the one direction. So here we have a biaxial tension. So you see it is a air pressurized tank for in which we have a pressure gauge. So in this we will be having the stress in the two direction. So in the z direction sigma z, and in the circular direction it is sigma theta. So this is a different kind of stress, hoop stress, but it is tensile in nature. So this we will learn when we will study the cylindrical shells or the spherical shells. So you see here, fish, it is in water. So if we take this as a stress element, so it is putting a compressive stress. Okay. So this is because it is in the hydraulics, so we call it as a hydrostatic compression. So now this engineering strain, yesterday we have learned what is stress, what is strain. So you see, this was the original L0, that is a piece which is having a length L0 and width W0. So when we apply a force, so it takes, it stretches like this in both directions. So here it is delta by 2, and here it is which is equal to del L by 2, and here it is delta by 2. So you see in the longitudinal direction it will be this. So the strain, because it has been decreased, okay, so it is minus, and here it is increased, so it is tensile strain. So tensile strain is positive, and the lateral strain which is decreased, it will be negative. So wherever there will be tensile strain, the lateral strain is bound to occur. Then we come across the shear strain. So this is a original element with us. So we apply these forces, this one in the opposite direction. So when we apply like this, so we can measure this angle, and this gamma is equal to tangent theta. So this theta by 2, because it is very small, so we can represent it by theta. Okay. So strain is always dimensionless. Then linear elastic properties. So simple tension test. So the linear elastic, we have linear strain, you see. So modulus of elasticity, yesterday we have learned. So modulus of elasticity, also known as the Young's modulus. So by Hooke's law, the stress is directly proportional to strain. And if we remove that sign of proportionality, so we get this expression, and E is our modulus of elasticity. So now the Poisson ratio, it is a lateral strain upon the longitudinal strain. So it is a property. So we denote this either with mu or nu. This is the symbol mu. So it is linear. So for metal, the Poisson ratio is 0.33. For ceramics, it is 0.25, and for polymers, it is 0.4. So normally it varies from 0.3 to 0.5, the value of the Poisson ratio. So E, the unit is GPa, and nu is dimensionless. So these are the two properties. One is the modulus of velocity, and another is the Poisson ratio. Now, property from bonding. Suppose this is one end is fixed, and we have a bar which is having a length L0, and the cross-sectional area is A0. Okay. So when it is this force F is applied, so the length is increased by a small amount, that is delta. So F upon A0 will be nothing is equal to E into this. How it has come? We know that modulus of velocity E is equal to the stress upon strain. Now stress sigma is F upon A0, and strain, it will be the change in length upon original length. So when you put this value here, it will be there. So in the case of the bonding, it is because of the surface energy. So you see unstressed length, smaller elastic modulus, and this curve gives the larger elastic modulus. So it is the curvature at R0. So E is larger if E0 is. Now, what are the other properties? So we have other property, elastic shear. So shear is denoted by the shear modulus, that is G. So it is in the same way, the shear stress is proportional to the shear strain. So if we remove this symbol of proportionality, so then it is tau is equal to G into gamma. So therefore, modulus of rigidity, or we call it as a shear modulus, it is tau upon gamma. Okay. Third modulus is known as the bulk modulus, which is denoted by K. So K is equal to it is hydrostatic stress divided by the volumetric strain. So this delta V is known as volumetric strain. We denote it with epsilon B. So it is equal to change in volume divided by the original volume. Okay. So this is, so again it is linear. So there is a special relation. So we have the three moduli. One is E, that is modulus of elasticity. Another, we have the shear modulus or modulus of rigidity. Or should we write it here? Modulus of elasticity. This is shear modulus or modulus of rigidity, and K is our bulk modulus. So we will derive this relation. So these two relations are very important. So you must remember them all the time for solving the numericals. So these are the special relations for the isotropic. So if we compare the Young moduli, so for ceramics it is highest, then for metals, and then for e-polymer. Okay. So if you see here, so our steel lie here. So it is around, as I told yesterday, it is 210. So it is 200 to 210, 240. So these are the other, alloys, copper alloys, zinc, silver, gold, aluminum, magnesium, tin. So it is lower. Okay. So it is in GPA. 1 GPA is 10 to the power 9. So this range is for the polyester. Okay. This is for the carbon fibers. And for the diamond, you see it is further high. Okay. So it is composites, graphite, ceramics, and composites. So this is a way we can compare the our modulus of elasticity. Now, useful linear elastic relationship. So this we have developed earlier also. We can develop very easily that sigma is proportional to the strain. So sigma is equal to E into strain. So this strain we can write L0, that is, sorry, L, or should we write, is, sigma is F upon A, F upon original area, that is A0. So change in length is delta L divided by L. So that will give you the strain. So from here, you can find the delta L or delta L. Delta L is equal to F into L0 divided by E. So this is the same relation which is given here. So from here, the change in lateral change, that is this, in this direction, because this is when it is compressed, so it is increased. Okay. So it is like this, and nu F into original width upon the area. Okay. So you can put this value, so you can find it out, because the nu is equal to minus delta L on the longitudinal. So you can keep this value and you can find it out. So in the torsion, so this is a shaft which is having a diameter that is 2R0, L0 is this. So this you will learn. We will drive this expression and we will find out this angle of twist which is given by this. So larger the elastic moduli, minimize the elastic deflection. Now plastic or permanent deformation. So at lower temperature, T is smaller than T met by 3. So in the simple tension test, if you see, we plot a curve between the stress and the strain. So elastic, initially it is like this. Then here, after this behavior is elastic plus plastic at the larger stress. Okay, and then when we remove the load, it comes back. So this much is the permanent set, or we call it as a plastic strain, and this is a state of affair. So permanent plastic after the load is removed. So you see it has not come along the same way. If it is perfectly elastic, so it should come back on this line, but because of the imperfections and all, there is some plastic deformation takes place. So this is a permanent set, or we call it as a plastic strain. But then what is the yield strength? We have discussed yesterday. We have talked of this term, sigma y. So stress at which the noticeable plastic deformation has occurred. Okay. So you see here, uh, uh, up to this point, there was elastic deformation. But after this, we have seen that the deformation has changed and it has increased till here. If you draw a perpendicular from this place, it is so much only. But from here to here, for the small change, the deformation is much larger. You see, this is much larger. So this means that by application of the small load, the material has started flowing or it has given up. The literary meaning of yield stress or yield is it is it has given up. Okay. So when sigma p, or sorry, epsilon p is 0.002, so the yield stress is bound to occur. So you can see here. Okay. So it is 0.002. So engineering strain. So the stress corresponding to this point is known as the yield stress or yield strength. Then we have talked of ductility also. So which is also known as percentage. EL means elongation. EL means elongation. Elongation. So plastic tensile scale failure. So ductility represents the plastic tensile failure. So percentage of elongation is final length minus original length divided by the original length into 100. So it is like this. We have taken a specimen of length L0 and A0 is the original area of the cross section. Now we have applied the force, tensile force in this direction, and this material will be stressed and uh, it will break into the two pieces, and this uh, phenomena is known as necking. So there is decrease of area and we also call it as necking. So AF is the final area and LF is the final length. So which is uh, greater than L0. So that's why if we take the percentage of this, that will give us the percentage elongation. Okay. Similarly, to measure the ductility, we have another ductility measure. So that is the percentage reduction in area. So we can call it as reduction percentage reduction in area. So A0 is the original cross section and AF is the final cross section divided by A0. So it gives us a percentage reduction. So that means there are two measures to define the ductility. If we want to measure the ductility, we have to calculate the percentage elongation and the percentage reduction in area. So they are often comparable. So reason the crystal slips does not change material volume. Percentage elongation in area is greater than percentage elongation in length, possible if internal void forms in the neck, if the voids are formed. So here we see, if we plot, so smaller percentage reduction in the length. So this is for brittle. So this we have seen, this curve is for the brittle material. And if percentage elongation is less than 5% for the brittle material. Okay. Larger percentage elongation if ductile, if the percentage elongation is more than 5%. So this is an important slide. Then the another slide, the another property, important property we have seen, that is the toughness. So it is the energy to break a unit volume of the material. It is measured by the approximate area under the stress strain curve. So if you see, this is a stress strain curve we have taken. So for the ceramics, you see, this area is smaller. So smaller toughness is there for ceramics. This is a larger toughness for the metals and the composites. Okay, and this is a smaller toughness unreinforced polymers. Okay, so this way you can see how to represent the toughness and how to represent the percentage elongation. Now another important property is the hardness. So it is an resistance to permanently indent a surface. It is like this. Suppose you take a metal piece and you try to scratch it with some pointed nail or pointer, or you want to abrade it, want to, make some impression. So it is a resistance of that particular material to avoid the or to resist the permanent indentation. Indentation we define it like this. Suppose this is a metal block, and we apply a load by a say a ball, steel ball. So when we remove the steel ball, so it will make a small impression like this. So this is nothing but this is indentation. This cavity which is formed, it is known as the indentation. So you can see here, larger hardness means the resistance to the plastic deformation or cracking in the compression, and better wear property. So suppose a 10 millimeter ball is there, okay, and if we apply a load from 1 to 1000 gram, so it will make a impression or indentation like this. So if you measure the size of indent after the removal of load, then you can find out the hardness. So this we learn in the hardness test. So smaller indent means larger hardness. So this is a scale. It has been adapted from a book. So for the most plastic, brushes, aluminum alloy, so hardness is increasing in this section. Then easy to machine the steel. So this is for aluminum alloy. This is for plastics. This is for steel. Then filing is hard. Then cutting for cutting tool. This is for filing. File is an instrument, or it is a tool, or you can say it is a manual tool, which is used to make the surface smooth. So this you have seen, must have seen in the workshop, in your workshop class. Then we have the nitrided steel, so a special purpose steel on which the heat treatment of the nitrate is done. So we say the nitrided steel, and then the diamond is the hardness. So this way the hardness increases. So In the summary, we can say we have tried to learn stress and strain. So they are the size independent. First thing very important. Measures of load and displacement respectively. Elastic behavior. This is a reversal behavior. Often shows a linear relation between stress and strain. So we have seen the different terms. So to minimize the deformation, select a material with a large elastic modulus, that is E should be large or G should be large. The plastic behavior, so this permanent deformation behavior occurs when the tensile or the compressive uniaxial stress reaches sigma y, or sigma y is the yield stress which we have defined. Then toughness, the toughness is the energy which is needed to break a unit volume of the material. And ductility, it is a plastic strain at the area. So I think you must have understood the basic concepts of the different properties of the material and the concept of stress and strain. So in the next lectures we will go much into deeper concepts and the derivation part. So let me try. I have tried to put one video which I could not run it yesterday. So let us see this video. So this video is very informative. So
Let's get started. Strength is a measure of the stress a material can withstand. Two different values are typically used to define the strength of a material, the ultimate strength and the yield strength. Let's define them by taking a look at the stress-strain curve obtained from a tensile test. The ultimate tensile strength of a material is defined as the maximum stress, which is reached during the tensile test, corresponding to this point on the stress-strain curve. It is the maximum stress the material can withstand during a tensile test. The yield strength is defined as the stress at which a material begins to deform plastically. Stressing a material beyond its yield strength will result in permanent deformation after the load is removed. Many structures and components are designed to ensure that they only deform elastically. This makes the yield strength a commonly used criterion for defining failure in engineering design codes. It is possible for failure to occur at stress levels well below the yield strength if the applied load varies with time. This failure mode is called fatigue, and I will cover it in a separate video. For some materials, the transition from elastic to plastic deformation is not clearly defined. In these cases, the yield strength can be defined using the 0.2% offset method. This involves drawing a line with the slope equal to Young's modulus and shifting it 0.2% to the right on the stress-strain curve. So far, we have only discussed strengths in the tensile direction. But what about the compressive direction? For ductile materials like mild steel, the yield and ultimate strength are very similar in the tensile and the compressive directions. Tensile tests are usually easier to carry out than compression tests, and so compression tests aren't often performed for these materials. For brittle materials like concrete and ceramics, however, the material strength is much larger in compression than in tension. I will talk about why this is the case later on in the video. First, let's look at some examples of strength values for a few different materials. Tensile yield strengths are shown for ductile materials, and ultimate compressive strengths are shown for brittle materials. Graphene is the strongest material to have ever been tested. It is a two-dimensional material made up of a single layer of carbon atoms arranged in a hexagonal lattice and linked by strong covalent bonds. Defect-free graphene has an ultimate tensile strength of up to 130 gigapascals, or 19,000 ksi. I've mentioned material ductility a few times in this video, so now is probably a good time to define it properly. Ductility is a measure of the ability of a material to deform plastically before fracture. Let's return to our stress strain curve. Materials which undergo large amounts of plastic deformation before they break are called ductile materials. These materials fracture at very large strains. Mild steel and gold are examples of very ductile materials. Materials which fracture at very low strains with little to no plastic deformation are said to be brittle. Glass and ceramics like porcelain are examples of brittle materials. Because they don't deform plastically, the concept of yield strength is irrelevant for brittle materials. There is no defined transition point between ductile and brittle behavior. Typically, a material which has a strain at fracture of less than 5% is considered to be brittle. Now that we have covered what ductile and brittle materials are, let's return to the question of why brittle materials are much stronger in compression than in tension. There are two factors at play. The first factor is that tensile loads tend to encourage the formation and propagation of cracks, whereas compressive loads do not, as illustrated here. The second factor is that in brittle materials, very little or no plastic deformation occurs to redistribute stresses at existing flaws. This means that large stress concentrations build up at the crack tip, resulting in fracture. In ductile materials, plastic deformation occurs, which relieves these localized stresses. Ductility can be dependent on temperature. A lot of different types of steel, for example, are ductile at room temperature, but become brittle when the temperature drops to below the ductile to brittle transition temperature. This transition temperature is an important design consideration because ductile failure is normally preferred to brittle failure. One very famous example of brittle failure is the Titanic. The icy waters of the North Atlantic are thought to have caused the steel of the ship's hull to drop below its ductile to brittle transition temperature, resulting in catastrophic brittle fracture. Toughness is the ability of a material to absorb energy up the fracture. It can be calculated as the area under the stress strain curve. If the area under the stress strain curve is large, the material will have high toughness, and so will be able to absorb a large amount of energy before fracturing. For a material to have high toughness, it should have a good balance of both ductility and strength. Low strength materials and brittle materials tend to have low toughness. A related property is resilience, which is the ability of a material to absorb energy when deforming elastically. It corresponds to the area under the stress strain curve, but only within the elastic region. Materials with high resilience are well suited for applications where plastic deformation is to be avoided. To summarize, the yield strength of a material defines the stress at which it begins to deform plastically. The ultimate tensile strength defines the maximum stress which is reached during the tensile test. Ductility is a measure of the ability of a material to deform plastically. Toughness is a measure of the ability of a material to absorb energy up until fracture. And resilience is a measure of the ability of a material to absorb energy while deforming elastically. That's it for now. If you enjoyed the video, please remember to subscribe.
So I think you could have enjoyed this lecture. So thank you very much for a patient listening.